Hi, everybody. I want to talk a little bit about light and quantized energy before we get started with our unit this week. What is light? I hope that you understand that light is a form of electromagnetic radiation and that it can behave in two manners. It can act um, like a wave, and it can also behave like a flux of photons. Whenever we're looking at it behaving as a wave, we want to be able to distinguish some important components of a wave. We need to understand that a wavelength is the distance between the two consecutive peaks in a wave, and we use the lambda symbol to represent that. And that the frequency is how often that wave is passing a given point in a specific amount of time. And we usually dictate that by talking about it in 1 second. So we use the symbol nu to represent frequency. Here's a wonderful picture of the electromagnetic spectrum, which you should be familiar with this spectrum. This goes a little bit more into detail. I love the fact that it gives the frequencies in our scientific notation, and then we can also see that pictorially as a representation of how those waves appear to be behaving in space in that particular amount of time. So if we look here, we can see on the left-hand side that we move from radio waves all the way to gamma rays. You should know that X-rays and gamma rays and ultraviolet light are much more intense forms of electromagnetic radiation, and certainly much more damaging to our skin cells. What we really want to look at right now is the visible portion of the spectrum, because that's what we're going to be focusing on for a little bit of our conversations and our initial activities that we're going to be doing. If you notice here, the visible spectrum makes up all of the colors of light here, and as all of those blend together, we know that creates white light. What's important to look at as well is I want you guys to note here our wavelength. We measure that in nanometers, and if you notice, we have a scale that goes from 700 to 400, with 400 being on that violet spectrum of color, and then also being closest to ultraviolet light. And if you look on the left-hand side, you can see that our wavelengths are 700 nanometers in length and is more indicative of our red color, and it is closer to the infrared light. So what is that saying? I hope that you are sparking some thought in your mind here, because what I'm hoping that you're getting from this is that 400 nanometer wavelength is a smaller wavelength. It is closer to ultraviolet light, which is much more dangerous to our skin cells. Therefore, it has a greater frequency, as can be noted by looking at the frequency symbol there, and that above the pictures. And that our red light has longer wavelengths because of the 700 nanometers, and that you should also note that it has longer wavelengths. So therefore, the energy involved in that is also less because the wavelengths are longer. And I also love here, like this little picture, giving you an idea of the size of those wavelengths in space. So I love radio wave thought. If you see here that radio waves are really we could think of those in terms of the size of people all the way to the size of large buildings. So radio waves are really huge. They're very low energy. They have very long wavelengths. And then as we move over, you can see here that as we moved from radio to microwave to infrared to visible and on, you can see that the picture to dictate the size of those waves is moving from macroscopic to microscopic items. Here you have ant representing microwaves, and as we move further over to the right, you can see that we have things that would require a microscope in order to visualize those items. So use all of those, use this picture, reflect back on this to think about the relationships between frequency, energy, and wavelengths. So the electromagnetic spectrum, it's not a new term for you, but know that it includes all forms of electromagnetic radiation with differing frequencies and wavelengths and energy. Hi, baby. Good night. Sorry, y'all. I just had a visitor. So, when we look at the visible spectrum, we know that it encompasses all of those wavelengths of light that represent the colors that we see. We'll talk a little bit more in detail about the diagram on the bottom right here because that's a lot more abstract when we think about light and we think about how it behaves with one another and we think of it in terms of additive, subtractive, and whether we're dealing with pigments that are absorbing light or light in general. Okay, so we really were just discussing here um, the the wave nature of light, and then we're going to move into looking at how it behaves as a particle. So we know that it propagates through space as a wave, and it does move at the speed of light. Do you know what the speed of light is? If you don't, go ahead and take a moment after the video and look that up so that you can be thinking about what the speed of light is and what it means. Okay, so this is something I like to kind of talk about in class, but let's go ahead and think about some of the relationships between frequency, wavelength, and energy. So, when a frequency of a wave increases, then the wavelength itself decreases. Remember, it's happening more often over time. So, when that is occurring, that is an inverse relationship. As one is going up, the other is going down. So, that makes that an inverse relationship. Now, frequency and energy, as the energy of a wave increases, therefore the frequency of that must also increase. So, because as the energy increases, we know that the frequency increases, which means the wavelength is happening more frequently over a period of time. Those are directly related to one another. Now, wavelength and energy. So these two properties are inversely related. I didn't give you an answer to this part or an explanation. I'd like you to describe that in your own words before we meet again, okay? Now, we're going to go ahead and talk a little bit about light acting like photons. So, in the early 1900s, some of the things that scientists observed was that certain elements emitted visible light when they were heated with a flame. And you guys are getting an opportunity to actually conduct these experiments yourself in class. So, what they discovered is that light can also behave like a particle. And whenever light of certain frequencies shine on a metal surface, then sometimes electrons are ejected from that surface. And so what they discovered is this was called the photoelectric effect. And so as metals were heated, what happened is they emitted certain frequencies of light. And so at different temperatures, the color of the metal was a different color. And that color is related to the energy absorbed by those electrons before they were ejected from the surface of that metal. Oh, we can talk a little bit about that later. That's not a huge deal. Okay, Max Planck. So he's the one who observed this emission of light from hot objects, and he decided to call that quanta. And so what that means is that energy can be emitted in very small specific amounts. That's called quanta. And that a quantum is the minimum amount of energy that can be lost or gained by an atom. And we're going to get into quantum energy here shortly. Now, Albert Einstein, I know you've heard of him. He's the one that proposed that light had a dual nature. He called it the wave particle duality. And this is whenever we coin that term, that photon. So a photon is a massless particle that carries a quantum of energy. Remember, that's a small specific amount of energy that is being carried by that photon. It is unique.